Hi, I'm Herb Gross, and welcome once again to Gateways to Mathematics, where our discussion today will center on the solutions for the problems in Self-Test 10, Form B. And let me apologize in advance. There are a couple of misprints in the first edition of the answers, and I will point them out as we go along. The big emphasis, by the way, in this lesson will be twofold. One is to apply what we learned in Module 9 about constant rates to measurement. But in doing this, we're making a heavy emphasis on the metric and English conversions, but that's only part of the lesson. So watch for when we shift from the metric system back into ordinary measurement. I will, of course, call this to your attention, but let's go to the board and start going through the problems. As far as I'm concerned, I don't want you memorizing conversion factors. If you want to memorize them, that's fine. If you learn the conversion factors by heart simply by repeated usage, sort of like knowing that 8 times 4 is 32 because you've used it that often, that's fine. But I will point out other ones as they're needed, but primarily the crossovers that we have between English and metric. As far as I'm concerned, you have access to this at any time. There are 2.54 centimeters per inch. There are 454 grams per pound and 2.471 acres per hectare. And with this in mind, let's just go over and start doing the problems. The first problem says, to the nearest foot, how many yards are there in 120 meters? And before I do the dimensional analysis, let me try to show you what thought process goes through my mind when I see a problem like this. You see, I'm given meters, and I want to convert to yards. I recognize the fact that meters are in the metric system, yards are in the English system, so I have to get myself to a crossover, and the crossover that I gave you is from centimeters to inches. So the thought process I go through before I even write anything looks something like this if I wrote it. I say from meters I can get to centimeters. From centimeters I can cross over into the English system by getting inches. See, I boxed this in to emphasize to you that this is where I'm crossing over from the metric to the English. See, from inches I can then get to feet, and from feet I can then get to yards. And don't get blinded by this. You see, as I do this, keep in mind that it's great to cross over, but that on either side of the bridge, on one side I have to know the metric conversions, and on the other side I have to know the English conversions. Once I have it in this form, now I put it into the dimensional analysis form. In other words, I want to get rid of meters, so for meters I bring in centimeters. Then I want to get from centimeters to inches. Do you notice the scheme here? Whenever there's a dimension I don't like, but what I mean by don't like, I'm not that kind of a person. By don't like means it's not the label I want for the final answer. See, when it occurs in the numerator, I put it into the denominator, and in the numerator, I put down any other noun that's related to it. See what I'm saying here? I get rid of the centimeters. I express centimeters in terms of inches, then get rid of inches, express inches in terms of feet, then get rid of feet and express inches in terms of yards. And by the way, it's not a bad idea to write it in this form before you even start putting the numbers in. See, now you've got the thing set up. Now you can say to yourself, okay, what's the relationship between centimeters and meters? Well, there's 100 centimeters to 1 meter. What's the relationship between inches and centimeters? That's the crossover. There are 2.54 centimeters per 1 inch. What's the relationship between feet and inches? There are 12 inches per 1 foot. What's the relationship between feet and yards? There are 3 feet per 1 yard. And by the way, some people make this transition in one step. They say there are what? 36 inches in a yard, and they save a step this way. I don't care which way you do it, but now you see you're in business, because what are you going to do? You multiply the numerators, that's 120 times 100, which is 12,000. Then you multiply all the denominators. What are the denominators? 2.54, 12, and 3. 2.54, 12, and 3. Now, from this point on, I basically will rely on the calculator. How do you do this problem? You take the 12,000, you divide by 2.54, whatever answer you get. See, it's a multiplication sign here, but it's in the denominator. So you divide by 12, then whatever answer you get, you divide by 3. And hopefully you'll be noticing that you don't have to change anything on your calculator. You just do these operations in succession. And you wind up getting, and this is interesting too, the calculator doesn't have the word yards on it, so you wind up getting 131.2335958. You have to remember that the label was yards. And if you don't remember that, how do you get that? See, you wouldn't have got this if the label wasn't yards, but remember, the meters have canceled, the centimeters have canceled, the inches have canceled, the feet have canceled. Yards is the label that's left. So it's yards, but the problem says find the answer to the nearest foot. Okay, well, when it says to the nearest foot, that doesn't mean they want the answer in feet. It's okay to leave the answer as 131 yards plus something. When somebody says to the nearest foot, I have students who do this all the time. If I say measure something to the nearest foot, and it's say 1 mile and so many yards and so many feet, they convert the whole thing to feet. Actually, when you say to the nearest something, it means that's the label you want for the fractional part. In other words, when I say measure something to the nearest foot, the answer could be in miles, but the fractional part is going to be in feet. So in other words, I look at this and it says what? It's 131 whole yards plus 0.2335958 of another yard, and of means times 1 in this case. So now I remember that there are what? This is the English system. I remember that since there are 3 feet in a yard, the fractional part is 0.2335958 of 3 feet. And when I multiply that out, you see, I don't even have to use the calculator for that. See, this is 0.23. Forget the rest. 0.23 times 3 is 0.69. That's more than half a foot, but less than a whole foot. So to the nearest foot, I have what? The 131 yards plus 1 foot left over. In the first edition of the study guide, and I have to confess to this, I typed the whole thing myself, so I can't blame the typist. I just evidently got mesmerized, and I typed yards over here. In other words, the answer appears as 131 yards, comma 1 yard. It should be 1 foot. It's just a typo, okay? Now, problem number 2 is designed to show you that if you're memorizing, it's very, very easy to confuse 2 problems. You see, if we just look at problem number 1 for a second, all I'm going to do is interchange basically the words yards and meters over here. See, in this problem, I give you 120 meters and ask you to convert it into yards. In the next problem, I'm going to give you 120 yards and ask you to convert that into meters. And what I want to show you is that if you analyze this the way I've taught you, you can't make any mistakes this way, even if you feel a little bit insecure with the metric system. See, this says what? To the nearest centimeter, how many meters are there in 120 yards? So the thing goes something like this. I'm given yards, which is the English system, and I want to get to meters, which is the metric system. And the way I'm going to do that is to think through what my conversion factors are. I know that I can get from yards to feet and from feet to inches. Once I get to inches, I can cross over into the metric system. From inches, I get to centimeters. From centimeters, I can then get to meters. So now I do, and by the way, if we can pick this up, I just thought you might be interested in seeing this. If you look at this row over here, and you then look at this row over here, do you notice they're like mirror images of one another? In other words, you go through, if you read this row here from right to left, you get the row we had before. That's going to play a very important role when we get to algebra. When you start with, when you start with one and you want to get to the other, when you reverse your steps, you just do them, you just backstep. What do you call it? You just backtrack in exactly the reverse order of how you got there. And in fact, what's going to happen is that not only will you do this in the reverse order, but where feet and yards occur, they will occur as reciprocals. In other words, what's going to happen is, in the first problem, when we get to feet and yards, you'll recall that, in fact, I think we can even see it from here. Do you see how this thing ended? Yards were in the numerator and feet were in the denominator. And that was the last step in problem 1. Notice that in problem 2, the yards to feet becomes the first step, but instead of yards over feet, it's feet over yards. And as I tell you this to see the symmetry, I'm also trying to show you how easy it is to get these things mixed up if you memorize. But if you do it in terms of dimensional analysis, you're saying what? I want to get from yards to meters. So from yards, I get to feet. From feet, I get to inches. From inches, I get to centimeters. And from centimeters, I get to meters. Now I put the numbers in. See, 3 feet per 1 yard, 12 inches per 1 foot, 2.54 centimeters per 1 inch. And do you notice I don't have to worry about whether I'm multiplying or dividing. You see, for example, the 2.54 goes wherever the centimeters are. Centimeters is in the numerator, the 2.54 goes in the numerator. If centimeters were in the denominator, the 2.54 would go into the denominator. Now what do I have over here? Centimeters to meters is like cents to dollars. 100 centimeters equals 1 meter, just like 100 cents equals $1. Now I've got all the nouns in place. I double check to see if my label is right. I want the answer to be in meters, so I see what happens. The yards have canceled, the feet have canceled, the inches have canceled, the centimeters have canceled. I'm left with meters. So now I just do the arithmetic. My numerator is going to be 120 times 3 times 12 times 2.54 divided by 100. Again, using the calculator, the numerator comes out to be 10,972.8. The denominator comes out to be 100. I do the division. I get 109.728. And I have to remember the label. The label is meters. And here's the beauty of the metric system. You see, because everything is a decimal system here, the 109.728 meters could be written exactly as what? 109 meters. And then what do I have over here? 728 thousandths of a meter. But a thousandth of a meter is called a millimeter. So the answer would be 109 meters, 728 millimeters. And the only reason that's not the right answer is that the problem says round the answer off to the nearest centimeter. Centimeters are hundredths, so that means I want to go over here. Since there's an 8 here, that makes this a 3. So if I rounded this off to the nearest hundredth of a meter, it would be 109.73 meters, and that's the same as what? 109 meters and 73 centimeters. Just like if there was a dollar sign over here, $109.73 is how you tend to read $109.73. And this system goes on and on and on this way. Let's apply it now to a real estate problem. Let's suppose, again, that you're buying a lot of land in a country that uses the metric system. You're used to the English system. So the price is given per hectare, but you're thinking in terms of acres. So the problem says at a cost of $255 per hectare, find the cost of 63 acres. You see, what's happening is you want, basically what's happened over here, you're given dollars per hectare, but since you're buying, you understand what's happening over here? If I take dollars per hectare and multiply that by acres, there's nothing to cancel out here. You see, somehow I want to get from dollars to dollars per hectare to dollars per acre. And I thought I'd just like to show you a nice way that you can do this. See, if you want to get in any label, suppose you're given A's and you want to convert to B's. You can make up any noun you want over here. Call those C's. And A's per C's multiplied by C's per B will give you A's per B. You see, I take dollars per hectare, multiply that by hectares per acre, okay? The hectares will cancel, and that will tell me how many dollars it's costing me for an acre. That's the common sense way of doing this stuff, and I'm trying to show you don't have to rely on dimensional analysis, but basically, if you don't mind the dimensional analysis approach, what you're saying is, I'm going to have to take acres, which I'm thinking in terms of, convert that into hectares, then knowing the relationship between hectares and dollars, I'll convert hectares to dollars. And the way that comes out in terms of a fill in the blank is if you read the problem carefully, forget the rate that you're given. The problem says what? Find the cost of 63 acres. So you say 63 acres equals blank dollars. Then what are you going to do? You're going to say, okay, I want to get from acres to dollars, so I want the acres to cancel, and I want to bring the dollars in. Okay? The problem is I'm not given acres per dollar. See, if I were given acres per dollar, the problem would be all over. So what I'm going to do is what? In this problem, I can put acres in the denominator. The problem is when I read the given information, there is no monetary relationship between acres and hectares. But there is a monetary relationship between hectares and dollars. So I say, okay, I'll get rid of acres, bring in hectares, then I'll get rid of the hectares and bring in the dollars. So how do I do that? You see, I know I'm given that there are 2.471 acres per 1 hectare. And I'm also told in this problem that there are $255 per 1 hectare. Do you sort of get the idea of what we're trying to do over here? I'm converting from acres to hectares, then from hectares to dollars. What do? I multiply what's ever in the numerator. That's 63 times 255. I divide by what's in the denominator. And again, for those of you who don't like the fractional notation, in terms of your calculator, you read this as what? 63 times 255, and whatever answer you get, you divide that by 2.4371. And by the way, the multiplication and division can be done in any order you want. You could have taken the 63, divided that by 2.471, then multiplied by 255. And one of the things I would suggest you're doing, if you're new at using the calculator, is fool around with these things and see what things you can do and what things you can't do with the calculator. But in any event, with the calculator, I very quickly get that the answer is $6,501. $0.416431. I think I left out something in the wording of the problem. I'm pretty sure the problem said round the answer off to the nearest dollar, in which case, since this is less than half a dollar, the answer would be $6,501. Now, in problem 4, I matched that up with you, with problem 3, in much the same way that 1 and 2 match. Do you see what I've done now? I've interchanged the word acre and hectares. See, problem number 3 said, at a cost of $255 per hectare, find the cost of 63 acres. So now I've written what? At a cost of $255 per acre, to the nearest dollar, find the cost of 63 hectares. By the way, we mentioned in our lecture that a hectare is bigger than an acre. So if an acre costs $255, a hectare is going to cost more than $255. So if by mistake you just multiplied the 255 times the 63, whatever answer you got, that should tell you what? It's too small to be the right answer, because there are more than 63 acres in 63 hectares. But again, what are we going to do here? We're going to go from hectares to acres to dollars. And why are acres being brought in as the middleman? Acres are being brought in here because the price is given in terms of dollars per acre, not dollars per hectare. And you see in blue, I've simply emphasized the fact that we're switching from what? Metric to English. So now what do? I have hectares. To get rid of hectares, I put them in the denominator. I express hectares in terms of acres, so acres go in the numerator. Then I get rid of acres and bring in dollars. Now, after I've checked that the dimensions are right, now I put in the adjectives. There are 2.471 acres to 1 hectare. And how many dollars per acre in this problem? That's not, see, by the way, that's one you don't memorize. See, there are always 2.471 acres per hectare. An acre doesn't always cost $255. That's just true in this particular case. See, sometimes you have to read the problem to get the relationship. Other times the relationship exists independently of the problem. So in other words, what I'm really doing over here is I'm filling in the blank, saying 63 hectares equals blank dollars. Now I just multiply the numerators. This is a nice one. All the denominators are 1, so that makes it easy for me. I multiply the 63 times the 2.471 times the 255, and that gives me $39,696.61.5, which to the nearest dollar is $39,697. And you see how neatly the calculator helps me there? See, again, remember our lecture on the calculator, the good and the bad? The good part is that once you're down to here, you get the answer very quickly on the calculator. The bad part is if you don't know how to get down to here, the calculator won't show you how to do it. All right? Now, let's bring in a weight problem. See, so far we've done what? We've done length, we've done area. Let's do a weight problem. And I deliberately picked some very nasty numbers here. Well, not very nasty. There's a few little things I've done here. One is I want to show you that when an item is very, very small, I want to emphasize what a rate is. Remember we saw that there were over 28 there are over 28 grams in an ounce. So a gram isn't very, very big. See, $0.0097, that's less than 100th, that's less than a penny, isn't it? See, a penny would be 0.01. This is less than 1 cent per gram. And you say, well, why don't you round it off to 1 cent? Well, the problem is if I round off, that's a pretty good approximation. But if I'm going to be taking millions of grams, that can be a big error. So first of all, I want to show you that sometimes in business applications, you have to use fractional parts of a cent. You don't drop them. But at any rate, at what? 97 ten-thousandths of a dollar per gram. The problem says, what is the cost to the nearest cent of A, 2 pounds, and B, 2 metric tons? Again, I want to show you, I picked the 2 here on purpose. And the reason for doing that was I want to, again, emphasize the adjective noun. It's not that you're getting 2 of something. In one case, it's 2 pounds, and the other case, it's 2 metric tons. Now, notice that what gives me a problem in Part A is, do you notice that the price, the rate, is given in terms of grams. Grams is a metric measurement. But the problem asks me to find the answer involving pounds, which is an English measurement. So somehow, in order to get from pounds to dollars, I first have to get from what? Pounds to grams. And I've again circled that in blue to indicate that that's one of our conversion factors. You see, pounds are English and grams are metric. So what I do is I'm going to go from what? Pounds to grams, and then knowing how many dollars per gram, from grams I can go to dollars. So the way this is going to look is, I start with 2 pounds. See, I want the pounds to cancel, and I can express pounds in terms of grams. See, I use this picture over here to motivate this picture down here. See what this says? I'm going from pounds to grams, and from grams to dollars. Now I fill in the missing numbers. What's the relationship between grams and pounds? That's one of the ones I told you to memorize, or to look up. 454 grams to 1 pound. No more thinking now. Once I know that, the 454 is modifying grams, the 1 is modifying pounds. So I just put that in here. Now I come to this column. What's the relationship between dollars and grams? In this problem, the dollars are 0.0097 per 1 gram. So how do I solve this problem? The label is correct. I multiply all the numerators, and I multiply all the denominators. Since there are all 1s in the denominator, I can forget about that. My numerator is what? 2 times 454 times 0.0097. And that answer comes out to be 8.8076. But I have to figure out that the label is dollars, you see. And it says rounded off to the nearest cent, so it would be $8.81. You see, it doesn't sound like much per gram, but by the time you've bought 2 pounds, you're spending what? $8.81. The Part B is a much simpler problem, in a manner of speaking, because in Part B, we have a very lucky break. And before I get to that, let me go back to the wording of Part A and have you see what's starting to happen here. Suppose this problem had said, at a rate of so much per gram, find to the nearest cent the cost of 2 kilograms. Suppose that had been the problem. Would I need the English system for that? See, if the rate is given in the metric system and the amount is given in the metric system, there's no need to cross over. You see, what happened over here is that the rate was given in grams, and I was asked the problem in terms of pounds. See, if the problem had been at $0.0097 per pound, what's the cost of 2 pounds? I just would have multiplied the 2 by 0.0097. So I want to emphasize that when I get to the next part over here. See, first of all, I want you to review the fact, if you don't remember it, that just like a kilogram is 1,000 grams, 1,000 kilograms is called a metric ton. So what I'm going to do is, and I'm going to do this wrong on purpose to show you how you can fall into a rut. See, I say to myself, in fact, this is by accident. When I was writing this out, I put pounds in first and was going to erase it. Then I decided, why erase it when I can make this into a learning experience? See, from metric tons, I can get from kilograms. From kilograms, I can get to grams. From grams, I can get to pounds. And from pounds, I can get to dollars. Well, that's fine, except that in this problem, you're given dollars in terms of grams. See, in this particular problem, you don't need the English system. All you say is, look, I can convert metric tons into kilograms, can't I? See, metric tons go into kilograms. Then I can convert kilograms to grams, then grams to dollars. Okay? And basically, now all I have to do is what? I put down what? There are 1,000 kilograms per metric ton. There are 1,000 grams per kilogram. And there are what? $0.0097 per gram. So now in this case, I'm not even going to bother writing the answer out for you. I did want you to see what was happening. I'm hoping by this stage of the game you can take the calculator. Well, heck, why don't I do this for you? You're going to multiply by 1,000,000. See, to multiply by 2 million, you can first multiply by 1,000,000 and then double the answer, right? So to multiply by 1,000,000, you're going to move the decimal point 6 places. That's going to make this $9,700. Then you're going to have to double that. So you get an answer like $19,400. But the point I wanted you to see here is this is a very small number, isn't it? But you're multiplying it by a very big number. You see, by dropping this, do you see what would have happened? If I suppose I had rounded this up to be, suppose I said, well, 0.0097, isn't that about 0.01? If I had done that, you see, instead of getting 9,700 over here, I would have got 10,000. See, I'm going to be off by $300. Then when I take 2 megatons, I'm off by $300 twice. That's $600. You see, rounding off over here is going to cost me $600 by the time I get over here. That's a pretty serious error in an estimate. Well, not too serious considering that the cost is $19,000 anyway. See, the relative error isn't that big. But still, if you can save $600, wouldn't you like to save it? Sure you would. Okay? Now, starting with problem number 6, we take the metric system out of the picture, so to speak, and we talk about other kinds of rates. See, at a rate of 51 miles per hour to the nearest tenth of a mile, how far will you travel in 4 hours and 17 minutes? And the first thing I want you to learn about these problems is don't be afraid to make estimates. Whatever 4 hours and 17 minutes is, it's more than 4 hours but less than 5 hours. At 51 miles per hour, in 4 hours, you would have gone 204 miles. At 51 miles per hour, in 5 hours, you would have gone 255 miles. Therefore, since 4 hours and 17 minutes is between 4 hours and 5 hours, but closer to 4 hours, you're going to go between 204 miles and 255 miles, but closer to 204 miles. And if you really want to round off, you say what? 51 miles per hour to the nearest 10 is 50. 4 hours and 17 minutes to the nearest hour is 4 hours. So if I'm interested in a real rough estimate, 200 miles is fine. That's another hard question to answer. If I say to you, what's the exact answer, there's only one answer. If I say to you, give me an estimate, how can I mark that wrong? It's your estimate. It's like if I say to you, what's the chemical composition of water? See? And you say, I don't know. How can I mark that wrong? That's a true statement. See? But if I say, if I say, do you know the chemical composition of water? And you say no, that's a true statement. Unless I can prove that you do know it, in which case you're lying. But if I say, what is the chemical composition of water? And you say, I don't know, that's a true statement, but it doesn't answer the question, you see. So sometimes what I'm saying is when I say give an estimate, there's going to be much more than one right answer. The estimate is just meant to give you a feeling of confidence in making a decision. But the exact way of doing this problem would be, you say, okay, what I'm going to do is I'll take hours and multiply that by miles per hour. The problem is, you see, I can't cancel the hours in the denominator with the hours in the numerator because this is a mixed label. So what I have to do is I have the choice of writing this as, see, if I want hours in the denominator to cancel with something in the numerator, what's in the numerator also has to be in hours. So what I could do is I could take 4 hours and 17 minutes and write that as a mixed number of hours. See, 4 hours, of course, is 4 hours. The 17 minutes really means plus 17 minutes. A minute is 1/60th of an hour, so 17 minutes is 17/60ths of an hour. Now I can take what? 60 times 4 plus 17 over 60. So that gives me what? 4 and 17/60ths of an hour. Okay? That's what I have over here. But I can write this as a mixed number. 60 times 4 is 240, plus 17 is 257. I put that 257 over 60. That's now converted 4 hours and 17 minutes into hours. Now there's what? The hours cancel. In this problem, I'm given that there are 51 miles per hour is the speed. So now I get the right label. I multiply the two numerators, 257 times 51, divide by the denominator. Remember again, the calculator won't give me the label. I've got to supply that myself. I've seen people put down hours here. I've seen them put down dollars. The answer is what? 218.45 miles, rounded off to the nearest tenth. Well, you could drop the 5 here, or you could add it on. Either 218.4 or 218.5 miles would be acceptable answers here. The other choice is, suppose you're not comfortable with mixed numbers. See, isn't every hour equal to 60 minutes? So 4 hours would be 240 minutes, and 17 more minutes would be 257 minutes. In fact, look what happens over here. Remember, another name for a minute is 1/60th of an hour. So 4 and 17/60th hours is how many minutes? 60 times 4 is 240, plus 17 is 257. Don't put it over 60, because 1/60th of an hour is called a minute. You see, when you have this, you also have it that you have 257 minutes. And now you want to convert minutes to miles, and the way you're going to do that is what? You'll go from minutes to hours, then from hours to miles. And how do you do that? There are 60 minutes per hour. You're traveling 51 miles per hour. See, check the labels here. So the answer is going to be miles. And the part that I thought you might find interesting is, even though conceptually this was a different approach, what is the final answer going to be? 257 times 51 over 60. 257 times 51 over 60. Now let's look at a different kind of an application. Access time to a computer is $252 per hour, and the time is measured to the nearest second. How much will it cost to use the computer for 2 hours, 11 minutes, and 37 seconds? I'm going to do this problem slightly differently from the rest, because I want to just show you different ways of reasoning. I have students who read this as 3 separate problems. They say 2 hours, 11 minutes, 37 seconds, and they say, which problem do you want us to do? I thought what I might like to show you is how the distributive property works over here. I had never thought about this before, but what you could do is what? Find out how much it would cost to use the computer for 2 hours, find out how much it would have cost to use the computer for 11 minutes, find out how much it would have cost to use the computer for 37 seconds, then add them all up, and that would give you the total price. And by the way, before you even start this problem, notice that as an estimate, at $2.52 an hour, for 2 hours, it would have cost you $504. For 3 hours, it would cost you $756. And since you're using it for a little bit more than 2 hours, you expect that it's going to cost you what? More than $504, but closer to $504 than to $756. Now, suppose I wanted to find out at $252 an hour how much it would cost me to use this for 11 minutes. In other words, I want to fill in the blank. 11 minutes equals so many dollars. See, I can do all of this mechanically by dimensional analysis. I can say, look, I know the price in dollars per hour. So what I could say is what? From minutes, I will translate to hours, and from hours to dollars. So what happens over here is what? I have 11 minutes. I convert minutes to hours, then hours to dollars. And let me just forget this part for a moment. Notice that the part that's left over here is 252 over 60. And what would the label be? See, the label hasn't been canceled. See, the label here canceled with the label here. If I forget about canceling this, notice that just looking what's in the brackets here, the hours cancel. This is dollars per minute. In other words, if you took the 252 and divided that by 60, wouldn't that be dollars per minute? And your common sense tells you that, because at $250 per hour, since an hour is 60 minutes, that's $250 per 60 minutes. But this diagram here is taking the place. The dimensional analysis is taking the place of all of that for you. See, I could divide the 60 into the 252 and find out that it's really costing me what? $4.20 per minute to use that computer. Now I'm paying $4.20 11 times. So for that 11 minutes, it's going to cost me another $46.20. Okay? Now, how about the seconds? See, the problem is, if I want to multiply a rate by seconds, the rate has to be given in dollars per second. Otherwise, I have to convert. Well, notice that $4.20 per minute is the same as $4.20 per 60 minutes. 4.20 divided by 60 is 0.07. So it's $0.07, 7 cents per second. So if it's 7 cents per second, for 37 seconds, it will cost me another $2.59. So all I do is, this is the price for 2 hours, this is the price for 11 minutes, this is the price for 37 seconds. I add them up, and that should be the total cost, $552.79. By the way, once I know that I'm only paying 7 cents per second, wouldn't it be just as easy to say, look at, 2 hours is 120 minutes, there's 60 seconds to a minute, so 2 hours is 7,200 seconds. There's 60 seconds to a minute, 60 times 11 is 660. So altogether in 2 hours, 11 minutes, and 37 seconds. See my common denomination again? There are 7,200 seconds, 660 seconds, and 37 seconds. And if I add that up, that's what? 7,897 seconds. At 7 cents a second, multiply this out, there's the same $552.79. On the other hand, you might say, look at, the price is already given per hour. Why break it down into seconds? Why can't I convert the whole time into hours? And you can, because notice that 11 minutes is what? 11, see there's 60 minutes to an hour, so 11 minutes is 11/60ths of an hour. How many seconds are there in an hour? See, there's 60 minutes per hour, 60 seconds per minute. 60 times 60 is 3,600. So what you could have done over here is to write everything in terms of hours. See, 11 minutes becomes 11/60ths of an hour. 37 seconds becomes 36/100ths of an hour. Now, how do you add? You put everything over a common denominator, okay? Your common denominator here is 3,600. So you have what? The same, I don't know if you noticed this, the same 7,200 plus 660 plus 37 that we had before. But now you see, since the label is hours, you don't have, the 3,600 comes in here because that's how many seconds there are in an hour. Now the answer is going to be what? This many hours at $252 per hour. And by the way, if you ignored this part and just divided this by this, that's where you would get your 7 cents per second. But you see all the different ways of doing this problem? Okay, let's go on. We've got a few more to do. I looked this up in the cookbook. A tablespoon is 2 ounces. A cup is 8 ounces. By the way, here's an interesting thing. And in calculus, we call these parametric equations. You notice, in this particular case, both tablespoons and cups are defined in terms of ounces. Well, see, when two different numbers modify the same noun, their ratio is obtained by just dividing. See, 8 ounces divided by 2 ounces is what? 4 ounces. In other words, this measurement is 4 times as big as this measurement. Therefore, since these are aliases for these two, a cheating way of doing this problem is for me to recognize that a cup is 4 times as big as a tablespoon. In other words, this implicitly tells me that there are 4 tablespoons per cup. By the way, be careful here. Some students say 8 over 2 is 4, so they say 4 cups per tablespoon. No, the cup is the bigger one, so it's going to take 4 tablespoons to make the cup. But at any rate, the problem says you have a tablespoon, but no cup. Cup in cooking circles means a special kind of cup. It's not a coffee cup, not a tea cup. It's an 8-ounce cup, okay? It's a measuring cup. But you have a tablespoon, but no cup. And the problem is a recipe calls for 3 1/4 cups. You have a tablespoon, and you want to measure out the 3 1/4 cups using the tablespoon. And the trick here is there's 2 ways you can do this. See, first of all, the 3 1/4 cups as a mixed number is 13 cups over 4. Now, if we had made the observation that there are 4 tablespoons to a cup, you see, from cups, we can convert to tablespoons, okay? The 4 here cancels with the 4 here, and the answer is going to be what? 13 tablespoons. But if you didn't notice that, you can still use the table I gave you. You can say what? From cups, I can go to ounces. Why is that? Because 1 cup is 8 ounces. We're given that. And from ounces, I can go to tablespoons. Why is that? Because 2 ounces is 1 tablespoon. The cups cancel. The ounces cancel. I now have the right label. What happens over here? I can multiply numerators, multiply denominators, but in this particular case, I hope you recognize that 4 times 2 is 8. So the 8 in the numerator and the 8 in the denominator cancel, and the answer is what? 13. But that's the wrong answer. It has to have a label. 13 what? 13 tablespoons. Okay. Here's a problem for you. You have 53 kilograms of tobacco. That's a safe word to use. You have 53 kilos, and you're going to pack it into 2-pound bags. You see what's happened over here? A metric measurement, but an English container system. And the question says, how many bags are going to be filled when you filled up the bags, and how many ounces are going to be left over after the bags are filled? You see, if this had been 53 pounds, all you'd have to do is what? Divide the 53 pounds by the 2 pounds. You see, when the labels are the same, they cancel when you do division. You follow the argument here? If this had said 53 kilos of tobacco are packed into 2-kilo bags, then you would still divide what? The 53 by the 2. But since you have different labels here, see, 53 divided by 2, you see, would be 26.5. But kilograms divided by pounds would still leave you with a label of kilograms per pound. It wouldn't cancel. So the way we get around this, well, let's first of all, let me show you how to handle this without the dimensional analysis. Then we'll bring the dimensional analysis into it. I have 53 kilograms. I want to convert to grams. Remember, there are 454 grams to a pound. So from kilograms to grams, I simply multiply by 1,000. Then, once I've converted to grams, since there are 454 grams in the pound, I divide the 53,000 by 454, and that will give me how many pounds? And that's 116.7400881. Now, the easier way of doing that, rather than doing all these steps in your head, is to say, look, I want to get from kilograms to pounds. Why do I want to get to pounds? Because I'm packing things away in 2-pound bags, so I want to convert kilograms to pounds. So I say what? I know how to get from kilograms to grams, and from grams I can cross over to pounds. So I go what? Kilograms to grams, grams to pounds. What's the relationship? 1,000 grams is a kilogram. 454 grams is 1 pound. And now do you see how this does the same work for me that this did? See, what do I have over here? 53 times 1,000, which is 53,000, divided by 454, which is exactly the same thing I had up here. And now, if I do this out on my calculator, I get 116.7400881 pounds. But I've elected to write it this way because I want to convert to ounces. And the way I do that is I recognize that when nothing appears over here, I can interject the words of a pound. See, it's this decimal fraction part of a pound. And what's a pound? It's 16 ounces. So I have 0.7400881 of, meaning times, 16 ounces. And if I multiply 16 times this, I get 11.8414096 ounces. So what is 53 kilograms to the nearest ounce? It's 116 pounds and 12 ounces. Now, how many pounds do I put into a bag? 116. So at 2 pounds per bag, that's going to fill up 58 bags. And now what's left over after the 58 bags are filled? 12 ounces. And by the way, usually I find an excuse, like it was a typographical error or something, to explain why there's a wrong answer in the study guide. In the first edition of the study guide, the answer, instead of giving 12 ounces, gives 6 ounces. And do you know what I did? I was thinking of a different problem when I was working this thing out. I took the 116 pounds and 12 ounces and divided that by 2. And that gave me 58 pounds, 6 ounces. See, I was thinking 2 pounds per bag, but what problem did I solve? Basically, I solved a much easier problem. The problem I solved was that if 2 people want to split 53 kilograms equally to the nearest ounce, how much does each one get? And then the answer would have been, what? 58 pounds and 6 ounces. But I'm not dividing this by 2. Remember the physical part of the problem. The problem says you're putting 2 pounds into each bag. So I fill up 58 bags. The whole 12 ounces is left over to form that portion of a 59th bag. And by the way, many books tell you that there are 2.2 kilograms per pound. If we had rounded off that way, it wouldn't have been a gigantic error. But you see, 454 grams per pound doesn't come out to be exactly 2.2 kilograms per pound. If we had rounded off to 2.2, the problem would have been easier, because now we would have had what? 116.6 pounds. 6/10 of a pound is 6/10 of 16 ounces. 6/10 of 16 is 9.6. That rounds off to what? 10 ounces? But the correct answer was 12 ounces. In other words, with what little bit we threw away, it was enough to cause us an error of 2 ounces in the small amount that we were dealing with. If this had been 53 metric tons instead of 53 kilograms, the error would have been enormous. And now, the last problem is one I just threw in for fun, because I never knew what it meant. You ever hear somebody says, just put in a pinch of salt? I thought that was just an old wives type of thing. You know, a pinch, a dash. I used to get dash and dish mixed up so they wouldn't let me cook. And I said, put in a dash of salt, I put in a dish of salt, then blame the cookbook. But I never realized that pinch is a technical term. And I looked it up in a book. And this is what's funny. See, the reason I'm throwing this problem number 10, it's not that fantastic a problem. I threw this in because it was fun for me. I had never known what grains were. I didn't know what pinches were. So I decided to try to figure out, where did something like a pinch of salt come from? I mean, it sounds like a small amount. How small is it? So I just went to a book. And that's what learning is all about. Learning isn't memorizing. It's knowing enough where to find what you want and then having the logical ability to use it. I went to a book, and I found out that a grain is defined to be 1/7,000th of a pound. So that sounds scary. In other words, I reworded that to say there are 7,000 grains in a pound. Okay. Then I found out that the legal definition of a pinch is 20 grains. See? So there are 7,000 grains in a pound. A pinch is 20 grains. Then I took a box of salt down from a shelf I had in the house, and the weight of the box was given as 2 pounds, 5 ounces. That's another thing I never figured out, why they put it in that size. Okay, maybe they saw me coming. They probably had that there for 1,100 years and sold it to me. But now I decided, okay, a pinch is pretty small. How many pinches of salt would there be in this 2 pound, 5 ounce box? This is not a serious piece of research, but by the way, that's how research is done. You know, one of the problems with writing a term paper as a freshman is you're told what topic to write on. Well, as a freshman, how many topics are there that you're that knowledgeable about? Well, that knowledgeable about that aren't self-incriminating if you write about them. But basically, the idea is when you get to be older and more mature in your field, that's when you feel like writing. And when you feel like writing, that's when you feel like doing research. That's the time it's really important to know how to write a term paper or to know how to do research. I remember the first time they taught me how to use a library, the Dewey Decimal System. I was in the 4th grade. All I wanted was Captain Marvel comic books, and they didn't have them in the library. By the time I needed to use the library, I went to the librarian and says, what's this Dewey Decimal System? I didn't know what it was. See, I had learned something at a time in my life when I wasn't ready for it. Now, I'm just trying to show you in terms of this little pseudo-sophisticated problem, how you can research something for yourself. It wasn't a big thing, but I wanted to research how many pinches of salt there were legally in 2 pounds, 5 ounces. The problem is that since pinches were defined in terms of grains, and grains were defined in terms of pounds, I first decided to convert the 2 pounds, 5 ounces into pounds. And that's what? The 16 ounces to a pound, so it's 2 5/16 pounds, which as a mixed number, as a common fraction, would be 32 plus 5, 37 over 16. Now what did I do? I wasn't that comfortable with grains per pound, just like you may not be comfortable with centimeters per inch. See, I'm comfortable with centimeters per inch because I use them all the time. Well, not all the time, but when I'm working. You can just imagine that. I go home, family says, what's new today? I say 2.54 centimeters to an inch. I don't use it all the time. But basically what I'm saying is I don't have to think about that. But I had to think about grains per pound because that wasn't natural to me. So I wrote out the dimensional analysis myself. I went from pounds to grains, and then from grains to pinches. And I looked up what I found. I found out there were what? 700 grains, 7,000 grains in 1 pound. Then I found out that there were 20 grains in 1 pinch. See, I'm practicing what I preach now. See, I check my dimensions. The label is pinches. I multiply the 2 numerators. That's 37 times 7,000. I divide by the denominators. That's 16 times 20. So it's 37 times 7,000 over 16 times 20. That comes out to be 809.375 pinches. So to the nearest pinch, there are 809 pinches in a 2-pound, 5-ounce box. Now, I didn't have to use the dimensional analysis here. I could have said something like this. I could have said, look, there are 7,000 grains per pound, so that means that's how many there are in 16 ounces. I'll divide 7,000 then by 16. That will give me my grains per ounce. But I have 2 pounds, 5 ounces, so that's 37 ounces. So I'm going to have to take what? The grains per ounce and multiply that by 37, okay? So multiply that by 37. That gives me how many grains I have. Then, basically, I'm going to do what? Since there are 20 grains to a pinch, I take this number and divide by 20. Dividing by 20 is the same as multiplying by 1 over 20. And the important point is, when I get down to here, do you notice that I have exactly the same thing that I had over here? See, I don't care which way you do it. I simply want you to understand what you're doing. You see, this was really a repeat of what you were doing in Module 9. I felt that the stuff in Module 9 was so important that we really should double up the module. So psychologically, rather than say we're going to make the module twice as big, I broke it down into what? Module 9 and Module 10. And all Module 10 was more of Module 9 applied to measurement. At any rate, worst case is I hope that you're now comfortable with dealing with rates of change. And now next time, what we're going to do is start Module 11, in which case, now that you're comfortable with constant rate of change, I have to shake that up a little bit and start talking about non-constant rate of change. But at any rate, you know how I'm going to end this again, don't you? Study hard, right? Have fun, stay young.